Hey Charles, how's it going? Tired, yeah. It's that time of the semester. I feel like it's that time of the semester all semester. It's always a grind.
I have a question.
Yeah.
There's something outside of coursework. Just for this ECS thing.
Okay.
Let's see. Is this thing?
Oh yeah, yeah. Uh-huh.
I noticed there were some dates. This stuff. I don't know if you know.
Yeah. I'm actually one of the mentors for that thing. So basically what it is, are you familiar with the idea of like a hackathon?
No.
And so it's
I heard of it, but I don't know something.
So basically, you're going to be given a prompt. So the prompt for this one is very, very wide. And so it's basically, we want to solve a social justice issue using engineering.
Yeah.
And so you're going to have to come up with an idea of, something that you can make. It has to be relatively practical. They're very loose about what practical means.
By make, what do you mean make? Like,
So you're just going to come up with a concept. And so you're not actually going to be physically making anything, but just a concept. And I'm guessing it's going to involve like probably like CAD models to some degree, maybe some prototypes, like very simple prototypes. It's very loosely defined. I'm honestly like not exactly sure either because I got voluntold to be part of this. And we had a meeting and then we had a lot of questions and they didn't have a lot of answers. And so they said it has to be practical. But the idea is that, you're gonna come up with an idea and, and then you're gonna present it to a panel of judges and then they're gonna rate your idea on some mystery criteria. And if you win, you get some money. And so,
that sounds insane.
Yeah.
Okay, I was formula team was talking about it.
Yeah.
Because we could use it for our formula club.
I think so. The idea is that the money would actually be used to launch the idea. And so the first prize is I think $800.
Yeah.
But I think, and so originally their plan was just to have all of it go towards whatever project that is to kind of launch it by next year. But $800 is also like no amount of money at all.
Right.
And so we're trying to make it so that like the students actually get to keep some of the money and so they can actually use it towards the project or for whatever that they want to. And so we're still kind of in the planning stage of it. And so we're still kind of figuring it out. But the idea is that, you have to solve a social justice issue using some kind of engineering solution. And so actually there was a senior design project. I don't remember if it was last year or the year before that, where they kind of designed this kind of mobile showering station. So that would be kind of a good candidate for that. And so it'd be something. And so they didn't actually get to build it because that was the year the pandemic happened. And so the idea is that, to kind of help keep homeless people clean is to kind of design something that's cheap. You can kind of tow it behind a car and to kind of give people a chance to kind of get clean and get maybe rid of any infections, stuff like that. Okay. So something like that. And so I think that's kind of the example that I've been kind of telling people. So it has to be has to kind of help some kind of social justice issues.
I'll bring it by my team because she's a woman member saying that maybe like because it's like good horror is like breaking down social stereotypes from like women can be so also like minorities because like from that's like a lot of Spanish Asian other ethnicities in there.
The project itself has to solve some kind of issue. Yeah, I mean, we can talk about it more. I think it's probably talking about offline. That's probably better. And we need to get more information on it too. So yeah, so I mean, the information. I know they're planning to have an information session in a couple of weeks. So I think it's going to be like Monday, the Monday of the week before Thanksgiving. So I think it's the 14th. Okay. Yeah, and so they're going to host an information session about it. And then all I know is that I'm supposed to advertise it and mentor some of the teams. But they also didn't give us any rules. So it's like, what's stopping us from just designing some big ass solar panels and put it over the North Pole and solve the energy crisis and climate change? Which are, I guess, not practical. I'm like, how do you define practical? Yeah. Use your best judgment. But yeah, let's talk. Let's talk like next week, and hopefully I have more information about you.
Yeah. Thank you.
Yeah. Oh, interesting. That's cool. I mean, just going to Disneyland at 4 in the morning is cool. All right, it's 5:30. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today? Oh, not good. Yeah, so we're on the eve of the project, or not the eve, the post project class, and so I saw that most a lot of people turned in their project over the weekend, so thank you guys for that. Wait a second. Wait, what? The project. So I haven't started grading them yet, and so but my plan is to have them all graded by the end of the week. And so this week I'll be very busy because I kind of took a quick scan and I saw that everyone wrote very long, very interesting reports, and so reading all of them is going to take me a while. But I'm glad. I'm glad, and so it shows me that you guys are putting a lot into this class, and I always appreciate the passion. And so it's going to be a long week, but it's going to be a good week. And so, but don't expect them to be graded before. I'll try to get done, but by Thursday. I think Friday is a bit more realistic, and so I think I'll probably have them done by Friday, and then we can talk about it on Tuesday after that. Right? 29 pages. Oh my goodness. Okay. All right, and so now that the midterm project is done, we can go ahead and pivot towards some other stuff. I know that was kind of dominating kind of the class for a while. And so the first announcement I want to make is that I posted a homework set, and so this will be the only problem set in the class, because most of the other assignments that I give you guys are ANSYS activities, and so this is going to be the only one where you're going to have to actually work out some problems by hand. Right? And so I posted that on Canvas kind of before class today, and that's going to be due in 2 weeks. And so that's going to be due on Tuesday, November 15th by 11:59 p.m. Okay. It is time consuming, and so that's why I'm giving you guys 2 weeks to do it. And so I would definitely start now. You should already be equipped to do, I'd say 80% of it, just because, you know, we've been covering the direct stiffness method for the last few weeks now. And so you should be able to do most of it. It's just that the last of the beam stuff, you know, we'll finish up today and on Thursday. Okay. But I wanted to give you guys enough time to do it because, you know, these problems can be a bit time consuming. So if you have to look at kind of lectures from 2 or 3 weeks ago to kind of remind yourself, then that's, you know, I would go ahead. And then after that, the next kind of the next big thing in this class, now that the midterm project is done, is the midterm exam. Okay, so we do have one exam in this class. Okay. And the content for the exam is going to be just based purely on the direct stiffness stuff. And the plan is to have the exam in class on the last day before the last class that we'll have before Thanksgiving. And so this is going to be on Thursday, November 17th in class. All right, and so these two things are very closely related. And so what you can expect on the exam are problems that look pretty much the same as on the homework, except probably a little bit easier because you don't have that much time on the exam. Okay. And so I try to do that. And so whenever I give an exam, I always try to make the problems pretty consistent with what I have on the homework. And so if you can do the homeworks, then I'd say you're in great shape for the exam. Okay. And so start working on the homework. If you have questions on it, you know, definitely let me know. And I'm more than happy to answer. Right. So it's not open notes, but you will be allowed a cheat sheet. So what I always allow in my exams is a single 8.5 by 11 sheet of notes. You can write on both sides. You can write whatever you want on it. The only thing I ask is that the cheat sheet be readable. You can type it too. Yeah, typing is fine, but no magnifying glasses. So I don't want you to type it in like 3-point font and then come into the exam with like a magnifying glass. And so, you know, none of that. You have to be able to read it kind of with your naked eye. Okay. And so, you know, it's a bit of a pivot. And so, you know, I know we were kind of doing pretty heavy answer stuff, but so this is kind of the theoretical part. And I wanted to finish all that before Thanksgiving. So then after that, you just focus on the final project, because right after we take the midterm exam, you know, I know people are going to start working on the final project. Okay. And so we'll actually talk about the final project specs probably sometime next week, so you can start thinking about it. But basically the final project is going to be a repeat of your midterm project, but you can choose the subject. And so you can choose kind of the CAD model that you work on. You can choose the subject, but you're going to be basically applying the exact same process. Okay. And so I know it's going to be a little bit of a short lead up, and so I think, you know, you'll have about a little bit over a month to work on the final project, but it's going to be just more of the same stuff for your midterm project. So it's just that you can apply it to whatever you want. Okay. Right, and so you know, a lot of announcements today, just because, you know, we are kind of making a transition. But are there any questions on any of this that I can answer? Okay, all right. So let's go ahead and get started today. And we're going to pick up where we left off last Thursday, which is on beam equations. Okay. Oh, question. So will we go over how exactly to bring personal SolidWorks into ANSYS? Yes. Yeah, so we'll be reviewing. We'll be going over that once we start talking more about the final project. A question: do I suggest to have a model the size of a toy? I think it helps just because it's easier to visualize that way. But you can also do bigger stuff as well. And so there's really no limitations. The only limitation is that you have to have a CAD model for it. And you can get a CAD model from somewhere online too. It's not something that you have to do yourself. Yeah. Also, yeah, I know the licensing is an issue, but even for big objects, sometimes you don't need as fine a mesh on bigger objects. You know, if the deformations and the stresses don't vary all that much too. Yeah, we can talk more about the final project probably on Tuesday. I'll give you guys a break from ANSYS for a while. Okay. Beam equations. And so this is the last, I would say the last chapter in our direct stiffness unit here. And it's all about how can we apply the direct stiffness method to solving for beam deformations. Okay? So beams are quite different from the elements that we've looked at before. So we've looked at spring elements, we've looked at truss elements, and even though springs and truss bars are quite different from each other, they deform in basically the same way. So they can basically only just be compressed or stretched. Okay? Beam elements, on the other hand, are elements that can deform perpendicular to its length. And so we call that deformation in the y direction. And so that's d1y, d2y. Okay. And they also are considering rotations as well. Okay. So we have theta 1, theta 2. Okay. And so what we covered last time was we covered the element stiffness matrix for a beam. So if you have a beam, you can define its element stiffness matrix like this. Okay? And so we have E I over L cubed. Okay? And then since our beam here has 4 degrees of freedom, we can basically solve for 4 things on a beam, then our element stiffness matrix also has to be 4 by 4. Okay? And so our beam element stiffness matrix was 12, 6L minus 12, 6L. 6L squared minus 6L, 2L squared minus 12. So that's what our beam element stiffness matrix looks like. Of course, if we relate this to the nodal degrees of freedom, we have d1y, theta 1, d2y, and theta 2. All right. And so, based on this beam element stiffness matrix, we can then apply this to our direct stiffness method. But remember, our direct stiffness method is just, the method is always exactly the same. The only thing that changes here is what we apply for the element stiffness matrix. Okay. So let me kind of remind you of the steps that we take. Okay. And so whenever we're solving a finite element problem by hand, and actually, the ANSYS uses this process as well. It's just the way it accomplishes it is different. Okay. Okay, so step 1 is to label the elements and nodes. Okay. So that's most of the time done for you. Step 2 is to compute element stiffness matrices. For each element. Okay. And so basically you're going to be computing, the entries above there. Okay. Okay, step 3 is to assemble the global linear system. And so remember, we want to put all of the element stiffness matrices into a single framework so that we can actually solve it. Okay. Step 4 is to apply boundary conditions. Okay, so the boundary conditions are going to modify our global linear system. And step 5 is to solve it. Okay? Or in other words, step 5 is MATLAB's time to shine. So once you kind of set up the system, that's about as far as you need to take it by hand calculations. And step 5 is, we turn it over to MATLAB to solve it for us. Okay. All right, and so let's do an example. And this time we're going to put numbers in it, and so we can actually see it in action. And we're going to go through this whole process. Okay. And what's going to be interesting about this example is that we're going to combine beams and springs. Okay. 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 So let's consider the following beam. All right, question. So for the midterm, are we going to be able to use MATLAB as well, or just go up to step 4? Yeah. So for the midterm, there's going to be no computers, and so you're just going to have to take it up to step 4. Okay. And so what I'm going to check basically is if you set up the global linear system correctly. Yeah. All right, so let's say that we have a long beam like this, and I'm going to split it into 2 elements. And so we're going to have element A on the left and element B on the right. Okay. We'll say each of these beams have equal length, and the length is going to be 3 meters. So let me go ahead and start labeling the nodes. And so we'll call node 1 attached to the wall. Node 2 is going to be right in between elements A and B. And node 3 is going to be at the very end of the beam. Okay. But at the end of the beam here, we're going to say that this is also being supported by a spring. And so it's a beam that's kind of supported by a spring at the very end. Okay. And so we'll call this spring, we'll call that element C. And the point at which the spring is attached to the ground, we'll call node 4. Okay. All right, and so let me define the parameters for the elements. And so we'll say that elements A and B are identical. And so the Young's modulus is going to be the same for both. And so we'll say the Young's modulus is 210 gigapascals. Okay. The moment of inertia for the beam is going to be 2 times 10 to the minus 4 meters to the 4th. And then for the spring constant for element C, we'll say that this is equal to 200 kilonewtons per meter. Okay. So that's the configuration for the problem. But we also need a load. And so let's say that we have a load being applied directly on node 3. We'll call that load P. And we'll say that P has a magnitude of 50 kilonewtons. Okay. All right. And so based on the information given in this problem, let's use the direct stiffness method. Let's use the direct stiffness method to compute the nodal displacements or nodal deformations at each of the nodes. Okay. Okay. All right, so we have a fairly standard problem here. So we have three elements. 2 of them are beams. and we're going to go through that entire process. Okay? Any questions on the setup for the problem? Our question. So how would the answer change if we did not use node 2? That's a good question. And so, what Roman's asking basically is that, we have a long beam here, and we basically split it into 2 elements. And so the question is, if we just consider that just one very long beam with a length of 6 meters, how that would change the solution, right? And so the biggest difference is that you're not going to be able to compute the deformation here at node 2, right? And so part of the reason why we split it up is so that we can compute the deformation in the middle of the beam. And so if we kind of make it all one beam, we only get the deformation on one end, but on one end it's a fixed support, so we know that's going to be 0 anyway. And then on the other end, and so by putting a node in the middle, we are able to compute the deformation kind of midway through the beam. But another benefit it gives us is kind of the same logic that we have in terms of meshing. And so you can see here that, if we split this into 2 elements, that's almost like we're having a mesh with twice as many elements as opposed to 1. And so it's actually going to make our result at the end of the beam actually a bit more accurate as well. Okay? And you can keep going with this. And so you can keep actually splitting this up into more beams. And so you can split this up into 2. And so we have 4 elements there. And that'll give you more and more accuracy. But it's a question of, how much work are you willing to do versus how much accuracy that you need. So, and so basically the more elements you have, the more data that you'll get, but also the more accurate your solution will be at the cost of doing a lot more work than before. Okay. All right, so let's go ahead and start applying the direct stiffness process. And so step 1 is already done for us. And so we've already labeled all the elements and nodes. And so let's start working on, step 2. Okay. Okay, so let's compute the element stiffness matrices for each element. And luckily for us, elements A and B they have the exact same properties. And so, we only have to compute them once. Okay. Okay, so let's go ahead and compute those values. I'm not going to fully compute this just because the numbers are they're kind of nasty in this one. And so just like I did in the last example we did on Thursday, I'm going to leave it in symbolic form and then kind of wait until the very end to plug in the numbers. Okay. But if you want, when you're doing these problems, if you want to plug in from the beginning, that's fine too. Just kind of be prepared to work with some pretty gnarly numbers, okay? Because especially for this one, you can see that here that we have gigapascals, and so that's basically 210 times 10 to the 9th, which is pretty gnarly compared to some other stuff. Okay. All right, so we have Ka, and so Ka, this is for beam A, and so we have EI over L cubed, and this is going to be multiplied by the 4x4 matrix, so 12, 6L minus 12, 6L. And then element A, of course, is going to be connected to nodes 1 and 2. And so we say that it's going to be multiplied by D1Y theta 1, D2Y theta 2. Okay. We're gonna have the same thing for KB. And so KB numerically in the element stiffness matrix, they're all going to be exactly the same. Okay. And so, again, you can plug in the numbers if you want, but it is quite messy with this one. So it is a little bit cleaner to leave it as the symbols. But remember, element B here is going to be connected to nodes 2 and 3. Okay. And so we need to reflect that in the solution vector here. Okay. All right, so those are the element stiffness matrices for A and B. I think what's probably more interesting is just the degrees of freedom that they're acting on, okay? And then we have the element stiffness matrix for element C. Okay? So element C is a spring, okay? It's been a while since we've seen a spring, but remember, its element stiffness matrix is just a 2 by 2, okay? Which is a site for SORIs for all the 4 by 4 element stiffness matrices that we've been working with. Okay. And this is acting on nodes 3 and 4. Okay. And remember, the spring, because it's kind of vertically upwards, it's only going to act in the y direction. So that's why we say that the degrees of freedom for element C are d3y and d4y. So those are our 3 element stiffness matrices. And so, next step is to, assemble this into a global linear system. Okay. All right. Any questions on this? All right. So let's go ahead and assemble now. Okay. So let's go ahead and pull the assembly together. Okay. This one's going to be a little bit different. And so, normally we have an even number of rows and columns. Okay. And so we're going to have 2 degrees of freedom for node 1, 2 degrees of freedom for node 2, 2 degrees of freedom for node 3. But node 4, you can see here that we only have 1 degree of freedom. Okay. So we don't have a theta 4 for node 3 because, node 4, because node 4 is only connected to the spring. Okay. It's also directly connected to the ground. And so it's actually not going to, it's actually just going to be zeroed out anyway. But, in case you're wondering, why there's no theta 4 row is because, there's no beam connected to node 4. It's only a spring. Okay. All right. So let's see how this looks like. And so because of this, our global linear system here is going to be 7 by 7. Okay. So let me go ahead and draw that out. Let me start with the forcing vector. We have F1y, M1, F2y, M2, F3y, M3, and then F4y. And then we stop right there because we don't have any M4. Okay. And then in the columns here, let me write out the columns. We have D1y, D1, D2y, D2, D3y, D3, D4y, theta 4. Oh, no theta 4. Sorry. Okay. y, theta 1, d2y, theta 2, d3y, theta 3, and d4y. All right, so there is our global linear system. Okay. 7 rows, 7 columns, and a lot for us to fill in. All right, so first thing we're going to put in is element A. So element A is going to be nodes 1 and 2. So let me go ahead and box that off. So that's element A. So that's going to go into that box right there. Element B here is going to be nodes 2 and 3. And so we're going to go ahead and box those rows and columns off. Go a little bit higher on this one. It's tough to squeeze all that in there. And then finally, we have element C. So element C is nodes. Well, it's not exactly nodes 3 and 4 because the spring is not going to contribute to theta 3, right? The spring only contributes to D3y and D4y. Because remember, the spring element stiffness matrix is only 2 by 2. And so there should only be 4 entries in this global stiffness system that go along with that. Okay? And so we're going to have it in the location of D3y, D3y. Okay, so we're going to have this slot right here. And then D3y, D4y, which is right here. Okay, same for the one down here. So D3y, D4y. And then finally D4y. And so because a spring, the spring does not contribute to theta 3. All right. So all that is all that's good. So let's go ahead and start filling in. So first thing I'm going to do, just to make it a bit easier for us, I'm going to put the beam constant out in front, and so that can be EI over L cubed. Okay. And so we start filling in. Get 12, 6L times 12, 6L. L squared, 6L, 2L squared. In the intersection, we're going to add together. And so when we add together, we get 24, 0, 0, and 8L squared. Okay. Repeat that here. I'm going to save the green spot for just a second because that one's going to be a little bit complicated. But I went ahead and filled in everything around that green spot. Okay. And so in that green spot there, we're going to add together the element from the beam, but also from the spring. Okay. And so that's where they have an overlap. And so we have a 12. Okay. And so the 12 is going to come straight from the, that comes from the beam element. Okay. And then we're going to add in the spring constant. Okay. And so you would think, you know, when we're looking at this this equation up here for the element stiffness matrix for a spring, it would just be the spring constant K. Okay. But remember that we're multiplying an EI over L cubed out in front. Okay? And so we have to account for that when we plug in our spring constant here. Okay. And so not just going to be K, it's going to be K multiplied by the inverse of what's in front. So we have K L cubed divided by E times I. Okay. And then we have minus K L cubed divided by E times I, minus K L cubed divided by E times I, and then K L cubed E times I. Okay. And everything else is zeros. There's 2. Okay. I just zoomed in a little bit just so you can see it a bit better. Okay. All right. Any questions on this? Does that make sense about, you know, why we multiplied K by L cubed over EI? Okay. All right. And so this is the assembly. Okay. And so this is you know, everything that we need for that. And so of course the next step is going to be the boundary conditions. And so let's go back up to the figure here to define our boundary conditions. And so we have two constraints here. And so we have a fixed constraint on node 1, a fixed constraint on node 4, and we have a single load on node 3. Okay. Okay. So let's go ahead and apply these boundary conditions to our system. So let's go with the constraints first. And so remember with the constraints, we're going to eliminate the entire row that's associated with the constraint. And so, you know, for node 1, we're going to eliminate this entire row up here. Okay. And this row right here. And we're also going to do the same for the last row because node 4 is also fixed. Okay. So let's go ahead and do that. And so I'm going to go ahead and eliminate. Oh, my iPad is not lagging today. Very good. Okay. And so remember, the way that we do this is we replace the entire row with zeros, except for the diagonal. And so for the diagonal, we're going to put a 1 there. Okay. And then on the left-hand side, or on the forcing vector, we're going to put zeros. Okay. And so let me go ahead and do the same thing for the last row. Right, and so that applies the constraints, and so that basically makes sure that d1y, theta 1, and d4y are all going to be equal to 0. Okay. And then finally, we have the loads, and so the only load that we have is going to be on node 3. Okay. And so node 3, we have a load of, what was it, 50,000 newtons or 50 kilonewtons. Okay. So we're going to have minus 50,000. Okay. And then for all the other nodal degrees of freedom, F2y, M2, and M3, we're going to plug in all zeros there because they don't have any loads being applied on those nodes. Okay. So the next step for this problem is just to plug in all the numbers. So actually, I consider this to be the most annoying part of these problems is just plugging in and putting it into MATLAB. You know, maybe I'm weird, but I like the process of getting the element stiffness matrices, kind of fitting them into the right slots, and then eliminating terms for the boundary conditions. All that is fun. What's not fun is plugging in a bajillion numbers into your calculator or a bajillion numbers into MATLAB. And even though MATLAB does do most of the computations for you, it's still kind of annoying to input all of this into MATLAB. Right? And so after, probably after about 10 minutes of just inputting numbers, especially the Young's modulus here is gigapascals, then you can get the solution. Okay? So if you solve this in MATLAB, we get the following results. And so we get d1y is equal to 0 meters, theta 1 is equal to 0 meters, okay, or 0 radians, sorry. Okay, so theta has no units. And so that makes sense because the node 1 was fixed, and so we shouldn't get any deformation there. d2y is a minus 0.02 meters. And theta 2 here is minus 0.012 radians. Okay. And next we have d3y and theta 3. So d3y is minus 0.0638 meters. And theta 3 here is a minus 0.016 radians. Finally, we have d4y, and d4y is 0 meters. So that's our solution. Any questions on this example here? Our question. So is there ever a case where you have more than one load at a given node? Yeah, absolutely. And so, what can happen here is that in addition to this y direction load right here, you can also have a moment. And so in addition to a load on node 3, you can actually apply a moment there as well. And so let's say that you have a torque, or you have a something you're twisting, and you're applying a torque there as well. Okay? So let's say that we have M3. This might be equal to 10 kilonewtons meters. Okay? And so in that situation, you have kind of both a load and a moment applied on node 3, and then to account for that in your system, you would just replace this entry right here, the M3 row, with that M3 value. Okay? And so what did I say? That was what, 10 kilonewtons meters? And so this would be 10,000. That's just So absolutely, you can have multiple loads on one node. And then in the 2D truss problems actually too, where remember in 2D truss, we split it up into X and Y. You may have a load in the X direction, and you may have a load in the Y direction. And you can apply both of them on the system just like that. Yeah. It's the same for ANSYS as well. And so if you, I know, I think some of you guys were doing that for your projects. I kind of scanned through that a little bit, but for activity 3, right? And so we had the signpost project. You know, you could apply multiple loads on the same location that represent different things. So you can have one load for like the wind that's hitting the sign, but you can also have a load from, you know, maybe you're hanging a boulder for some weird reason from a freeway signpost, and that can be applied there as well. Yeah. Any other questions on this example here? Okay. So one more thing I want to do with this example before we move on is compute the reaction forces. Okay. So if you remember, you know, we did this with the truss problems. Okay. And the idea with the reaction forces is that you want to compute, you know, what are the forces being applied at the locations of the constraints that are keeping the structure in static equilibrium. Okay. Okay. Because all the cases that we're considering are static cases, and so there's no movement, there's no acceleration or anything. So, you know, by definition of a static system, the sum of all the forces that are being applied on the structure should equal 0. And now that we're considering beams too, that means there's the sum of all the moments on the system will also have to equal 0 as well. Okay. Okay. And so if you recall, the way that we did this was that, you know, after you solve for the deformation solution, okay. And so after you solve for the nodal deformations, what you're going to do is you're going to multiply those nodal deformations by the global stiffness system before you apply the boundary condition. So basically in between steps 3 and 4 of the direct stiffness method. Okay. Right. So this is the step basically after assembly. So after you assemble all of the element stiffness matrices into the global system, you take that big matrix, you multiply by the nodal displacements, and that's going to give you the reaction forces. Okay. Unfortunately, I don't have it for this one because I was lazy and I forgot that this was part of the notes. And so I kind of already overwrote it. And so, you know, if you weren't lazy like me and you kind of rewrote the system after the boundary conditions, this would make the step a lot easier. But because I was lazy, I had to pay the price now. And so now I have to write the whole thing over again. Okay. And so if you recall, or if you're watching this on YouTube, maybe you can rewind maybe 20 minutes. And so you can see what it looks like. Okay. And so we would have a EI over L cubed And then we have this multiplied by a 7 by 7 system. So this is, of course, my notes for this page are really faded. And so we have 12, 6L minus 12, 6L, 0, 0, 0. And so that's what it would look like. Okay. So that was our global stiffness system kind of before we applied the boundary conditions. Okay. And so if you were, not lazy like me and you kind of kept this from earlier and you didn't completely override it with the boundary conditions, you can just pull it down. Okay. And then you're going to multiply this by the nodal deformations. And so everything in this vector you just computed before. And so all you would have to do is just multiply these two together. And so of course you would probably do this within MATLAB. And so if you can save kind of both matrices in MATLAB, but before boundary conditions and after boundary conditions, you might save yourself some time here. Okay. And so you perform this matrix vector multiplication and you end up with the nodal forcing, the nodal reaction forces. Okay. And it's always not a bad idea to check the nodal reaction forces. And so of course it's all a question of how much time you have. But if you're wondering, my deformations don't look quite right, then what you can do is you can compute the reaction forces and kind of do a sanity check. Because remember, when you compute the nodal reaction forces, all the forces, if you add up all the forces in the reaction forces, they should add up to 0. The moments they will add up to 0 too, but then you also need to account for the reaction forces too. But usually just checking the reaction forces is enough. Okay. Because what can happen a lot with these types of problems, where there's quite a significant computation part to it, quite a lot of writing too, is that you might miss a negative sign or you might mistype something in or not. Okay, and so there's a lot of room in these types of problems for I think human error. Okay? And so it's always kind of good to kind of check your work just to make sure that it's good. Okay, so one example for this that we can use for this problem is we can look at the deformations. Okay? And so if we look back at our problem, right, we had basically two beams and we have an applied force on the end. Okay. And so based on this geometry, what we can kind of expect is that the deformation here at the node where the load is being applied, that should be where the deformation is the highest because that's where the load is being applied. It's also farthest away from the fixed support here, which is kind of giving it a lot of stability. Okay. And so, what we should see is that the deformation should be greater here than, let's say, node 2, where node 2 should have less deformation than node 3. Okay. And so if we look at our solution here, and we look at D3y, we can see that D3y has a higher magnitude than D2y by about a factor of 3. Okay? And so that matches up. And so that's pretty consistent with kind of what we expect. Okay? And so when you're doing these problems, I know they're time consuming. I know they require a lot of writing, a lot of computations, but kind of always be checking your work. It's because you'd be surprised to see that you just miss one negative somewhere, and then that kind of throws off your entire solution. And so these problems are actually quite sensitive to things like that. Okay. All right. Any questions on this? Okay. All right. And so kind of the last kind of major thing that we'll talk about for beams is this idea of distributed loading. Okay. And so if you've noticed from all the direct stiffness problems that we've been doing so far, all of the loads have only been applied on specific nodes. Okay. In other words, all the loads that we've been considering have been concentrated on single points. And those points are kind of at the nodes of our system. Okay? This is a little bit different than how we do it in ANSYS, right? So remember in ANSYS, when we're applying our loads, we're applying our forces, we're applying our pressures, we usually want to apply this on as wide a surface as possible. So if ideally we apply this distributed on an entire surface, but if that's not possible, then we apply it along an edge, and in the worst case scenario, we apply it at a point. And so point loading or concentrated loading is usually kind of the least desirable thing that we want to apply in finite elements, but we've kind of been doing it in direct stiffness. Okay. And the reason for that is because the reason we're doing it in direct stiffness is because it fits kind of very cleanly into our global linear system. Okay? And so when we have a load that's being applied at a point, we just apply that load directly onto that point in the global linear system. Okay. And actually, that's not too different from how it's applied in practice. And so even when you apply a distributed load, a load that's distributed along an entire surface, what ANSYS will do is that it'll convert that distributed loading into loads applied at certain points. Okay. Okay. And so that fact is true even within ANSYS. Okay. All right. So the question now is that how do we go from a distributed loading situation to nodal loads? Okay. So basically, what we want to do is let's say that we have a beam like this. Okay. It's a simply supported beam. Where we have loads being applied on the entire surface. Okay, so it's distributed all throughout. Okay. So the question is, how are we going to go from this to a situation like this, where we have, we've taken the beam, we've discretized it, or we've meshed it into little beamlets. Where each of these is a node, right? And so instead of a load that's being distributed evenly across the whole surface, what we want to do is we want to convert it into loads that are applied only on the nodes of our mesh. Okay? And so the question is, how do we do this process? So beams kind of provide the best, I would say kind of the best setting for this, because we're considering deformations that are perpendicular to the beam. And so we can kind of distribute load kind of all across the beam, okay? And so kind of the key to this is this idea called work equivalence, which we're gonna leverage here. But that's basically the end goal. And so, whenever you have a distributed loading, you can't really directly plug that into a global linear system. And so you need to first convert it to nodal loads, just so that you can process it mathematically. All right, any questions on this? Okay, and so let's start. So we have about 15 minutes left, and so I think we'll kind of introduce this idea, and then we'll kind of hash it out on Thursday. Okay. Right. So the idea behind work equivalence is that when you apply a load onto a system, that load is going to cause the system to deform, okay, for an elastic structure. Okay? So that's kind of the basic tenet of almost everything we're doing in this class. Okay. And so when you kind of put it another way, you basically are saying that we have a force that's causing some kind of displacement in the system. Okay. And so if we multiply these two quantities, and so we take a force and we multiply by a displacement or some kind of deformation, we know what this is. And so this, if we look at the units actually for this, this has the same units of energy. Okay. And in fact, this is the exact formula for work. Okay? Probably the first time you're introduced to work in a physics class, or at least what I remember it. This is the formula that was given to us. When you have a force and you're applying it to move an object or to deform an object over a certain distance, we call that work. Okay. Okay, so let's use this concept and kind of apply it towards distributed loading. Okay. And so distributed loading is still a load, and so it's still a force, but that force is distributed over a certain area, okay? And so what we can first say is that distributed loading has units of force divided by some kind of length or some kind of area. Okay? And so if we think of like a pressure force is a force divided by an area. Okay. And so the units for that would be like, if we use SI units, it would be like newtons per meter square. Okay. Or if we're looking at a 1D case, and so we have a force that's distributed over a length, the units for that are going to be newtons per meter. Okay. And so if we wanted to compute the amount of work that the distributed force is doing, we can't just multiply it by the deformation. Okay. Because the units aren't going to match up. So remember, in order to get units of energy, you need basically Newton meters, okay? And that's basically the same thing as a joule, right? And so if we just multiply the distributed loading by that, we either going to get Newton by itself or Newton over meters, which is not the right units, okay? And so in order to get work from a distributed loading, we need to integrate the product of distributed loading and the deformation. And so what we can say is that the work done by distributed load, so we'll call that work distributed, this equal to, and I'm going to take the case of a force kind of exerted over a length. And so we're going to assume that the distributed force has a units of newtons per meter. Okay. Is going to be the integral from 0 to L of Wx. Okay, so I'll use P of X, where P of X, this is the distributed load. Okay. And so distributed load has units of newtons per meter. Okay. Multiplied by D of X, where D of X here, this is the, in this case, we're looking at beam. So this is the beam deformation. Dx. And so that integral, because of the dx here at the end, the dx is going to add another dimension of length to this. And so we have Newton per meter multiplied by the deformation. And so that's going to be like another units of meters multiplied by dx, which is just another units of meters. And so we end up with the right units here. Okay. And so, we're not going to do any calculations on it, but if you wanted to find the work done by a distributed force, like a pressure, you would do a double integral. Okay? So you double integral P of X, where this is maybe like a pressure, which is newtons per meter square, multiplied by D of X, dA. Okay. And so if you wanted to do kind of the same computation for a force distributed over an area, you would use the formula on the bottom. But we're not going to focus on that for this class, just because doing just one integral, you'll see, is already kind of enough. That's how you would do it in 2D. Okay. So go there. All right. Any questions on this? Okay. All right, and so that's the work that's done by a distributed mode. So I'm going to go ahead. I'm going to leave that alone for a second, and then let's look at a nodal system. And by nodal system, I basically mean a system where the loads and the deformations are being computed at the nodes. Okay. And so, for a nodal system, we have something looks like this. Okay. So here's our beam. I'm going to isolate the beam for a second, so no constraints. And so the deformations on this beam would be, let me use blue. Okay. So we have D1Y, D2Y. We have theta 1, theta 2. Okay. So this would be like the solution to a direct stiffness problem with beams. And so we would get, these 4 degrees of freedom. But in addition to that, to cause these deformations, we also have to have the loads. And so we have F1Y, F2Y, we have M1 and M2, okay? And so basically what we're saying is that F1Y, F2Y, M1, M2 are causing the beam to deform in the ways of D1Y, D2Y, theta 1, theta 2, okay? And so it's the same as before, right? So we have a load, and then we have the corresponding deformations that result from those loads. And so based on this information here, we can come up with a formula to compute the work done by these nodal loads as well. Okay. All right, so the work done by the nodal loads is going to be the product of force times deformation. Okay. And so we have F1y times D1y. Okay. And so that's the work done by F1y. And then to this, we're just going to add together all the other nodal works from all the other places. Okay, so we have F2y, D2y plus M1 theta 1 plus M2 theta 2. So we have two formulas here. So we have one formula that's work done by distributed loading. And then we have another formula here by work done by nodal loading. Okay. And so the key here is to note that, for a case when the nodal load, we want basically the equivalent nodal loads to distributed loading. Okay. Because remember, that's our goal here. So our goal is we're starting with the distributed load and we want to find the equivalent nodal loads. Okay. These two equations for the work have to be the same. And so we have work done by the distributed load. This is equal to work done by the nodal load. Okay. So in other words, integral from 0 to L, P of X, D of X, dx is equal to F1y, D1y plus F2y, D2y plus M2 theta 2 plus M1 theta 1. I don't know why I put M2 theta 2 first, but whatever. My hand is cramping, so that's it. That's it for today. You just say your hand's cramping. That's it, right? All right, and so we'll stop here for today, but we're going to pick this up on Thursday. So the idea basically is we're going to use this equation here together with an expression for d of x, and so that's kind of the mystery man here because we don't know what that is just yet. And so we're going to transform basically we're basically going to come up with a method to transform any distributed loading into nodal load. Okay. All right, so thank you guys for coming today. Remember, I'll have your midterm project graded by Friday. That's my goal. Hopefully by Thursday, if I have a lot of free time tomorrow, which I don't think I will, but we'll see. Okay, and I'll see you guys Thursday. So thank you guys. Yeah.
What direction is the deformation?
We'll go over that on Thursday. So yeah, we haven't defined the d of x yet. So yeah, Roman, I haven't yet. I haven't read any of them yet. I just did a quick skim just to see kind of how much work I have to do over the next couple of days, but I haven't read them yet. But, I will definitely let you know once I read this. Yeah, I'm looking forward to it though. Hey.
Good question.
Yeah.
Do you know when you'll announce the extra assignment for graduate students?
So the extra assignment for grad students, I should think of that soon. Next week. Yeah, so when it's usually like an extra aspect of the final project. So I usually have you do something like extra for that. I just haven't decided what that is. So yeah, when we talk about the final project next week, I'll have the extra assignment. Yeah. Yep. All right, Zoom people, any final questions before we wrap it up today? Okay. Okay. All right. So I'll see you guys on Thursday.